Hello, everyone, and welcome to Central Coast Astronomical member meeting. Tonight, we have our special guest, Dr. Ray Weymann. Before I introduce him, I want to let you know how this evening will go. The purpose for this meeting is to share this presentation. And what we'll do is receive the presentation from Dr. Weymann, and I will be watching for questions anytime during the presentation, and we'll save all the questions till the end. Send them anytime, and I'll be saving up all the best questions and interacting with you on the chat, moderating the chat as we go. And remember that to give me those questions, you can either type them right into the YouTube chat, or you can text them to 805-242-6415. Text, don't call. I'm going to be a little too busy to give you a call on the phone. Or you can email them questions at centralcoastastronomy.org. Remember, one of the benefits of watching from our YouTube is you could watch from a smart TV, a Roku, or device like that. So we set up the text number and the questions email so that you can do that from your phone while you're watching on your nice big screen TV, hopefully. So let me share with you a little bit about Dr. Ray Weymann. He is a retired astrophysicist with 40 years experience in teaching and research. His research interests have varied from the history of the early expanding universe to the atmospheres of stars, and combined calculations and observations with some of the world's most powerful telescopes, including the Hubble telescope. Since retiring and moving to Atascadero, California, his interests have turned to public education about science, especially concerning climate science and global warming. He has given dozens of talks to both students in science classes and adult groups with many backgrounds. His website on climate science is centralcoastclimatescience.org. He has also taken an interest in the challenges teachers face in our public schools in teaching math and science literacy, and has tutored students in both basic and advanced math courses at the high school and junior high school level. He attended Caltech as an undergraduate and obtained his PhD in astrophysics, I should say, from Princeton University. For many years, he was on the astronomy faculty at the University of Arizona in Tucson, serving for some of that time as department head and director of the University of Arizona Steward Observatory. He is a member of the American Association for the Advancement of Science and an elected member of the American Academy of Arts and Sciences, as well as National Academy of Sciences. So without further ado, Dr. Ray Weymann, I'll pass it over to you.
Well, thank you, Brian. Let's get started. Let's see if we can figure out how to share the screen. That seems to be working so far. Okay, the host is spotlighted. Well, that's gone. All right, well, thank you very much for your introduction, Brian, and greetings to all of you who are listening, and happy April Fool's Day. This object is not an April Fool's joke, although it certainly has fooled an awful lot of astronomers. I want to mention that Brian is taping this, so if you have friends who said, well, I'd like to watch it, but I'm busy, Brian will send out the link, and I will as well, so that those of you who couldn't manage this time can watch it. And as Brian mentioned, I do have a website, centralcoastclimatescience.org. And because we have way more material about this fascinating object than I'm going to be able to cover, I'm going to post an expanded version of what we're talking about tonight, and then I will let you know when that's ready to go. So let's get started then and see what we can do after that. Going forward here, if I can get my things going. Okay. I have to, first of all, to tell you that the topic I'm going to be discussing is far from my area of expertise. My expertise is in really other aspects of astrophysics, so I had to learn an awful lot from astronomers whose area this is their area of expertise. And so I want to acknowledge so many people who have given a lot of time explaining things that I knew nothing about to me. So here is a brief discussion of some of the things I want to talk about. I will be skipping over some of them, though. I want to first of all talk about how this object came to be discovered in the first place. Then I need to give you a little bit of background on what we think about the early history of our solar system, because that's relevant to ideas about this object. And then, as I say, this object called Oumuamua, which is a Hawaiian name loosely translated as scout or messenger. It was discovered in Hawaii, so that's why they've given it a Hawaiian name. And then after we go through some of these puzzles and surprises, because there is no really satisfactory explanation right now for it, people have come up with rather unconventional, or you might say out of the box explanations for this object. I'll talk about a couple of those. And then in part 5, we'll talk about some of the more natural interpretations of Oumuamua. I want to concentrate particularly on what it's made of and how it got its shape. And then, since we don't understand it yet, and for that particular object, we probably will never understand it, I want then to ask, where do we go from there to learn a little bit more about what other solar systems consist of? And we'll see that there are 2 very powerful instruments coming online, which should help us with that. And then finally, because one of these unconventional explanations has risen quite a large amount of controversy, I want to talk about whether what you might call scientific norms have been violated or not. So with that introduction, let's go ahead and talk about what's called the Pan-STARRS project and the discovery of this first object. The first object to enter the solar system from interstellar space. Well, the Pan-STARRS object was started so that astronomers could get a good inventory of the rocky little objects we call asteroids, most of which orbit between the orbits of Mars and Jupiter. And one of the reasons for doing that is that, as I think you all know from seeing maybe discussions about the demise of the dinosaurs, from time to time, some of these objects have struck the Earth. And if they're pretty large, they can really have disastrous consequences. And so the idea was maybe we should keep our eye open for an object which is likely to hit the Earth, with the possibility that we could send out a probe, not to destroy it, but maybe to nudge it off its course and thereby avoid the impact. And so that was done, and it gave rise to this object here, a telescope, which is sitting on top of the island of Maui, a mountain called Haleakala. And this is one of the 2 telescopes. It has a very large field of view, and it has a mirror diameter of about 80 inches. And it surveys a large portion of the sky visible from Hawaii several times a month. And in the background, by the way, you can see another mountain that's over on the big island of Hawaii, and that's Mauna Kea, where some of the world's most powerful telescopes reside. So how do these telescopes discover asteroids? Well, it works like this. An object that is moving in the solar system will appear to move against the background of the stars. So the telescope in this case is tracking the Earth's rotation, and so the stars appear as little dots here. But this little blurry line here is an indication that there is another object in our solar system which is moving relative to the background of the stars. So when you see an object like this, you can change the telescope tracking to track the object itself. And then, of course, that makes the stars appear to be little tracks. What I want to point out about this image here, this is it. It's just a little dot. You can't see any structure. One of my astronomy friends who may be watching tonight said, Ray, be sure that people understand in the advertisement about the talk tonight, that long cigar-shaped object, that wasn't a picture. That was an artist's rendition. We'll talk about how he got that idea. So it was just a tiny little dot. We have no idea directly what its true shape was. The other thing I want you to notice, though, is that whatever it is, it's not one of these big, beautiful comets that we are used to seeing blaze across the sky. You can't see any fuzz around it. You certainly don't see a tail around it. So it is evidently not one of these beautiful comets. The tail of a comet is caused by small particles which reflect sunlight, and glowing gases which are vaporized from the icy body of the comet itself, are composing what is called the coma, and then the solid little white dot is the nucleus of the comet, sometimes thought to consist of a combination of a conglomerate of rocks and ice. And when I say ice, I don't necessarily mean just water ice. It could consist of frozen carbon dioxide, carbon monoxide, methane, ammonia, that sort of thing. Okay, so what made that particular little blurry object so interesting? Well, it was fairly quickly apparent that in fact it was the first visitor to us from outside our solar system. It came zooming in at a velocity which was 26 kilometers per second. And that speed is far too great for the sun to be able to hold on to it from the sun's gravity. And by the same token, it meant that there was no way that this object could have originated in the solar system. There was just no way that it could have acquired such a kick. The sad thing, though, is that in fact, this object wasn't discovered until it had already passed by its closest approach to the sun inside the orbit of Mercury, as you can see. And in fact, it actually passed by its closest approach to the Earth. And it was already quite faint when it was discovered. For the astronomers who knew about magnitudes, it was about a 22nd magnitude object. So only could be studied with the largest telescopes. And then within a few days, it became very, very faint. And within a month, it was basically unobservable. So with that little background of the discovery, let me give you some information about the current notion of how our solar system came to be and a little bit about its constituents. It's believed that the stars in our galaxy, in what we call the disk of the galaxy, were formed in very dense clouds. And when I say dense, I mean dense by ordinary interstellar standards, composed of molecules of gas, mostly molecular hydrogen. And it can be very, very cold there. And so if there isn't a lot of high gas pressure, the gravity of that giant molecular cloud will cause the gas cloud to collapse, and little lumps in the cloud will form into stars. And so about 4.6 billion years ago, it's believed that the sun was formed probably in association with a few other stars forming a cluster. And then most of the material went into the stars themselves, but some debris was left behind in the form of a disk. And it was this disk which gradually formed into the planets, but not all of the material went even into the planets. You can see here Jupiter and Saturn, the giants, which were able to retain some gases, hydrogen and helium, and then Neptune out here. But beyond that, a cloud of smaller little particles, of which Pluto is the largest and probably most famous. All of these objects compose what are called the Kuiper belt, and they're icy bodies. And it's believed that soon after the solar system formed, there were a much, much larger number of these objects than there are today. And many of them, by interacting with the giant planets that wandered around quite a lot in the early stages of the solar system until their orbits stabilized. They ejected some of these objects to much further distances in the solar system. And indeed, perhaps it actually caused some of them to escape from the solar system, just as we think this object that we've just discovered was probably ejected from another star system having a debris disk of its own. And so some of these objects from the Kuiper belt got flung out, as I've said, to much, much larger distances. We measure distances in terms of what is called an astronomical unit, which is the distance from the Earth to the sun. And you can see that this cloud, more or less in the form of a sphere, consists of perhaps 10 trillion of these tiny little icy bodies. And it extends to 100,000 or so Earth-Sun distances. And in fact, that's considerable distance of the way to the nearest star. So you can imagine that because of the weakness of the sun's gravity out here, it's quite easy to dislodge some of these objects. And that's why we think that having objects coming in from other solar systems is not a terribly great surprise. However, there were some surprises, and I want to run through a few of them. The first one was the very discovery fairly quickly of Oumuamua itself. The reason for that is that people who make models of the evolution of the Kuiper belt and the Oort cloud thought that the number of ejected objects would be sufficiently small that given the short time that the Pan-STARRS project has been operating, we shouldn't have seen one yet. So it was a little surprising to find one such a short time, just a few years after this Pan-STARRS project began to be operating. So that was puzzle number one. Puzzle number two was, and this was a real shocker, it wasn't following exactly the trajectory that one would have expected just from the force of gravity itself. We can certainly predict the force of gravity with extreme accuracy. As you know, after all, we can send probes to Mars and Jupiter and even Pluto, after all. But although it was only a small deviation, the existence of a force about 1/1000th the value of the force of gravity was certainly acting on this. And so that's something that has really had astronomers scratching their heads to try and explain that. Another puzzle was the fact that it varied rather dramatically in brightness. Now, that's not unheard of in objects like asteroids, but the amount of variation of this object was in fact unprecedented. And astronomers plot that variation in brightness in terms of what they call a light curve. And this is one of those light curves. The amateur astronomers know about magnitude, but if there are non-astronomers watching, don't worry about that. This just illustrates the object at its brightest up here, and down here it was about 1/10 that brightness. So it varied up and down in brightness, and these are three very large telescopes, in fact 4 large telescopes, that observed it over this 3-day interval. And you can see that it was moving in a roughly periodic way, changing its brightness over one cycle about every 7 or 8 hours. And the most likely explanation for that is that if you look at an object like this happens to be an asteroid, which is one of the ones that we want to watch out for. It happens to pass quite near the Earth, about 4 times the Earth-Moon distance. And you see it has a rather irregular shape. And so if you can imagine that this is tumbling about, we might see more of the illuminated side here from the sunlight, giving us a large projected area. Whereas if this were the part that was facing us, then it wouldn't have such a large area illuminated by this sunlight, and therefore it would appear to be fainter. And so that large variation in brightness gave rise to that cigar depiction that I was mentioning. But that, in fact, is not the only possible shape. Another possibility is that it could have looked something like this. The important thing is that it is nowhere near spherical. Its long direction must be about 10 times or so its small direction, whether that's in the shape of a disk or not. Now, I want to, let's see if I can get back out of this screen sharing mode here. Hang on, let's see. I don't see, Brian, where we've got the screen sharing option.
I can go ahead and stop the share for you if you'd like.
Great, let's do that. Oh,
Okay.
I see, or screen sharing, stop the share. Got it. Okay, so I built this little stick figures here to explain what I mean by this. And if you can imagine that if it had a cigar shape, and this is the axis about which it's spinning, pointed like this, we only see this small little surface area, so it would appear quite faint. And then when it spins around this axis, you would see a large portion of the object facing both the sun and us as it happens, and then it would appear to be much brighter. But you can do the same thing if you want with something that's facing, spinning around this axis here. Now it would appear relatively faint, and then it would get bright again and then fade again. The question is, do we have any way of distinguishing between the two? And there is an argument in favor of this shape rather than this shape. And that has to do with the fact that if you assume that the object came in with a random direction of which way the spin axis could have been pointing, there's no reason to favor one direction over the other. It turns out this is able to account a little better for the variations in brightness that we saw. And that's why that we want to give some weight to considering that it's pancake rather than cigar shape, but that's not an ironclad argument by any means. Okay, so let's go back now to the screen sharing. Puzzle number 4, and coupled with puzzle 2, this is what really got people scratching their heads. I showed you in that image when it was just a little dot that it didn't have any tail and it didn't have any coma. And it's possible to detect certain gases that were normally present in comets, but in fact, none was detected. Now, the usual suspects are carbon dioxide, carbon monoxide, and water vapor. No observations were made of water vapor. There's only an indirect limit on the amount of outgassing from water vapor. There were limits on the carbon monoxide and carbon dioxide, and they weren't observed. And there is a limit on how much material could have been in the comet tail. The reason this is such a puzzle is because it's thought that the reason for this non-gravitational force, which is observed in many comets, is that the outgassing acts as a little exhaust, like you would shoot gas out of the tail of a rocket. You would give that an extra little boost. But none was observed, and I think coupled with the existence of this non-gravitational force, that has proved to be a real challenge. I'm just going to mention 2 other puzzles. I'm not going to spend too much time on them because I don't think they pose as severe a puzzle for explaining the object as the others that I've mentioned. The Spitzer infrared telescope measures infrared radiation, and it wasn't seen at all when they tried to detect Oumuamua. That says that the object can be terribly dull, because if it was very dull, it would absorb sufficient radiation from the sun that it would warm up and emit infrared radiation, and the Spitzer Infrared Telescope would have detected, and it didn't. But as I say, that's not an insurmountable puzzle, but it does play a significant role in one of the explanations for the nature of this object that I'll talk about. And number 6, its velocity happens to be almost exactly what we call the local standard of rest. The local standard of rest, if you think of a swarm of bees, let's say that the bees are leaving their hive and they want to go somewhere else and find a new hive. So you have all the bees swarming around. Each individual bee is moving around, but the swarm as a whole will have an average speed. And that average speed in the stars in the neighborhood of our galaxy is called the local galactic standard of rest. And these giant molecular clouds that I mentioned also appear to be moving at that local standard of rest. Some people have made a big deal of that. I think there are reasonable explanations for that that don't pose quite such a large puzzle. So those are the 6 puzzles. Let's just summarize them, and then we'll go on to some other explanations. The number of objects is greater than people expected, just based on the statistics of this one appearance. So let's remember that we're doing statistics. In this case, we're talking about the statistics of exactly one object, and that's always a little risky. There were definitely non-gravitational forces at work. It showed an unusually large variation in brightness. No tail or coma or outgassing was observed. Limits were set, but some observations, notably water vapor, simply were not made. It was a little shinier than you might have expected for some asteroids. And the host star, wherever that star was, ejected, presumably rather gently, this object, and that star must have had, by chance or because it has another significance, velocity that was very near the average of the swarm of bees. So because of these puzzles, there have been 2 unconventional explanations for what this object might have consisted of. And before I discuss the first one, let me say that I don't know about you folks, we haven't been paying perhaps as much attention to cleaning our hardwood floors as perhaps we should have been with all the pandemic stuff going on. But if you have been like us, not that careful about looking up around the little nooks and crannies of your hardwood floors, you might have come across something like this. This is called a dust bunny, and you can see that it's very, very fluffy, so it has very little mass, but it has, relatively speaking, a large surface area. And so something like this suggested an idea to a Spanish astronomer by the name of Amaya Morrow Martin. And she said, well, supposing that this object was made of tiny, tiny little ice grains, which are also very porous and fluffy. It's described as a fractal structure, and we can talk about fractals in the discussion period if you want to. But anyway, she thought it might look something like this. And the idea, it just like the dust bunny, by the way, so this idea has been called the cosmic dust bunny. It has a very large area, but very, very low mass. And that means that, relatively speaking, it could intercept quite a large amount of sunlight. But because it had so little mass, that intercepted sunlight, because of the radiation pressure exerted by that light, that perhaps could be the explanation for the non-gravitational acceleration. Well, that was a non-conventional explanation number 1. Explanation number 2 is really thinking way outside the box. And this idea is due to a Harvard astrophysicist by the name of Avi Loeb. And he said, well, look, I don't think that any of the explanations I've heard of are viable. And therefore, I'm going to suggest that what it is an artifact sent out perhaps tens, hundreds of millions of years ago, who knows, by some advanced alien civilization. It may be long dead by now, and whether directed randomly or deliberately to various solar systems. I think that maybe it could be accelerated by radiation pressure if this object here was made of extremely thin material so that it had a large surface area and a very small mass. And he called this the solar sail. So that was his idea. Now, there's certainly no way of proving this. I mean, we don't have a picture of it. That's the only way we would have known. And so Avi Loeb's argument is simply, well, I don't believe any of the other explanations that I have heard of are possible. And therefore, I argue in the following way. And he said, there's a quote from Sherlock Holmes, and it said, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. Now, it's my opinion that he hasn't eliminated the impossible. To be sure, there is no completely satisfactory explanation, which everyone is happy with, but by no means would I agree that all the others are impossible. So let's consider what some of these more, you might say, inside the box explanations are, even though I have to say those are quite unusual. And I want to concentrate on the two main questions. What is it made of? Is it made of water vapor? Is it made of solid molecular hydrogen? Or is it made of solid ice of nitrogen? So those are the three most recent suggestions for its composition, and I'll talk about its shape in a moment. And there are difficulties with each one. As I say, there are no direct measurements of water vapor, so we can't be sure that it wasn't outgassing water vapor. There is an indirect argument against it, but that can be gotten around if you say that this object had a slightly unusual chemical composition and coming from another solar system. Who knows? The big argument against the water vapor is that it's hard for this object to absorb enough solar energy during its path through the solar system in order to have enough energy to vaporize the solid ice and eject it as vapor. None of these things go through the liquid phase under these circumstances. It's what we call subliming. And it takes quite a lot of energy to sublime water ice compared to these other two. So that's, I would say, the difficulty with that, although I personally, I still kind of like this idea. If you stretch things and assume just the right shape and configuration and the orientation of the little jet of outgassing and so forth, you can make it work, but it is a bit of a stretch. Now, the other two models, the one about the solid hydrogen doesn't take very much energy at all to convert from solid to a gas. But in order to get solid hydrogen to form out of the gaseous molecular hydrogen, which we know is very abundant in these giant molecular clouds, it has to be cold. And I mean really, 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 really cold. So cold that it has to be almost the same as what you may have heard about, this bath of radiation we call the cosmic microwave background radiation. And that's very, very difficult to come by. Not impossible again, but you have to make exactly some special assumptions. And in particular, interestingly enough, you have to have little grains on which the gas can condense on, which also have this porous fractal shape that Omaya Mora Martin talked about for her cosmic dust bunny. So the problem there with that one, I think, is just getting the thing to form in the first place and getting a place that's so well shielded from all other sources of energy that you can get the gaseous hydrogen to condense into solid. The nice thing about it, though, is that it would be very difficult to observe outgassing. You just wouldn't have it detected. And then the third entree is the one involving solid ice of nitrogen. And there the notion is that in the early phases, for example, of the solar system, I described ours, where there were a huge number of objects in the Kuiper belt, and they were getting thrashed around and stirred up in their orbits by interacting with Neptune, for example. They would collide. And the notion is that one of them, like Pluto, for example, maybe other Plutos or Pluto-like objects, little collisions between Kuiper belt objects would knock a chip off the Pluto-like surface, which we know does consist on its surface of liquid nitrogen. Liquid nitrogen is thought to be a few kilometers deep. The rest of it is probably water ice, and then further down a rocky core. But without any question, there is some solid nitrogen ice. So that's one nice thing. We don't have to imagine some ice that we have never seen in the solar system. Again, I think the problem with that, as I read the paper, is that it's a little difficult to get enough of these objects. These people have done elaborate calculations on how many of these fragments should have been ejected, and they come up a little bit short, not a huge by a huge factor, but enough to be of some concern. And of course, none of these satisfy everyone. Each proponent of one of these three objects thinks that the other two guys are all wrong and they're right. That's the way science works until we get it all straightened out. Now, one thing is interesting is the question of how did it get this shape? Well, in the H2O model by two astronomers, they imagined that a comet went very close to its host star, and the tidal forces ripped that comet apart. And in the process of ripping it apart, little fragments of it were torn off, and they would naturally, according to their computer simulations, would have a shape of a cigar. And so that's where they get that shape. The other two folks here having these two models, by the way, when I say model, I don't mean that they build these things out of Tinker Toys or my own little models here of the disc and the cigar shape. These are mathematical models. But anyway, they construct these mathematical models, and they invoke what I would like to call the soap, bar of soap model for a shape. Now I think I know how to stop the screen sharing to do this other little demonstration. So if you go in your bathroom and you open up a nice bar of soap, it might have a shape something like this. Maybe this dimension is about 40% perhaps of this dimension. Now, if this thing is traveling through interstellar space and cosmic rays are bombarding it and abrading it away, and then it gets into the solar system, it's further abraded. If it's presenting randomly its face to the cosmic rays and the sun, since this has a larger surface area than this will naturally get abraded more than this area here, both this surface and this surface. And that will quite naturally eventually lead to a shape that looks something like this, as you will see by experimenting with an old and a new soap bar in your bathroom. So that's what I call the bar of soap model, and people have done elaborate calculations on that. So I think that's a rather nice idea. Let's go back to the screen sharing now. I have to once again, though, comment on this business of the statistics of one. Um, it is somewhat amusing to me that people have spent so much time on the statistics of exactly one object. I mean, you might say, well, my golly, we'd only observed a single object, and if it's just one of them, what are the chances that, in fact, we would find yet another one? And that's even more unlikely. And moreover, what if it was something else entirely different? I like to think that Mother Nature had a little sense of humor, because less than 2 years after Oumuamua was discovered, lo and behold, what did we find? We found this, another interstellar visitor, only this one was, beyond the shadow of a doubt, a comet. It wasn't a dust bunny. It wasn't a cigar. It wasn't a disk. It was a nice comet. And moreover, it was a bright comet. It was so bright that it didn't take pan-stars to discover it. It was discovered by a Crimean amateur astronomer named Borisov with his own telescope that he built himself. And it was about 1,000 times brighter than Oumuamua. It turns out also that this does have a slightly unusual chemical composition. Again, I don't consider that particularly amazing for something that came from an entirely different solar system. So that's maybe a lesson that we shouldn't take the statistics of one too terribly, terribly seriously. Now, I want to mention that I heard talk from a well-known astronomer who was an expert in planetary dynamics by the name of Scott Tremaine. And he gave a wonderful talk and it ended up talking a little bit about this alien hypothesis of Avi Loeb. And he dug up another Sherlock Holmes quote, which I think hits the nail on the head. And the second quote is this: "It is a capital mistake to theorize before one has data. Insensibly," that means nonsensibly, "one begins to twist facts to suit theories instead of theories to suit facts." So it isn't true that we don't have any data on this, but I think not nearly enough to reach definitive conclusions. So the question is, okay, so where do we go from here to get more data? And this is where I want to discuss the two very powerful instruments that we'll soon have online. For sure, I feel the LSST, which stands for the Large Synoptic Survey Telescope, or it's been named now in honor of astronomer Vera Rubin. She was the astronomer, by the way, who discovered the first convincing evidence for what we now refer to as dark matter. And that one is going up in Chile. I'll describe it in just a moment. And then the other one is the James Webb Infrared Telescope, which we hope will be launched sometime later this year. So let me talk about these two instruments. And for the members of the Central Coast Astronomical Society, you're accustomed, I think, to have telescopes which consist of two mirrors called Cassegrain-Schmidt. The design of this telescope utilizes three mirrors. This primary mirror here sends the light up here to the secondary mirror, down to a third mirror, and that third mirror brings the light, passing it through some correcting lens, sort of like Super Schmidt correcting lens, and to the focal plane. I mentioned this is 8.4 meters in diameter. This is a big mirror. To give you some feeling for just how big that is, here is the mirror blank before it was figured into shape. So you can see this is not a toy. This is a really, really big telescope. And one of the amazing things to me about it is not only do you have to figure these services to about a millionth of an inch in order to make perfect images, but that third mirror that I mentioned was actually carved out and polished from the same great big piece of glass, an amazing bit of technology. And in fact, that's going to be a very, very powerful survey telescope that will be super, super pan-stars. And the reason is that it too has this tremendously large field of view. You can see here that you would be able to fit 7 full moons. And this CCD camera, I think all of us are, you know that we have CCD detectors in our cell phones and all sorts of other things. This has 3 billion pixels. So it's a whopping camera, and it also poses a really demanding data acquisition and processing system. So that's one of the instruments, and I think beginning in 2022, it will begin to detect, we hope, more of these interstellar interlopers and tell us a lot more than we know right now. This is the James Webb telescope. You can see that it consists of different segments. There are 18 of these segments, and this has to be folded up in order to fit inside the launch vehicle, and then it will be launched, we hope, safely, and parked in a stable orbit called the L2 Lagrangian Earth-Sun system, and then opened up, and then each one of these segments has to be very, very accurately aligned with all the others. And it's designed to be particularly effective in the infrared part of the system, and it will tell us a lot more about these disks out of which planets and planetesimals form in other solar systems. So that's the story on it itself. But now I think that I would like to come to this issue of scientific norms. I mentioned Avi Loeb with this very unconventional explanation. I have to first say that he is a very gifted and highly regarded astrophysicist, very prolific and very imaginative. The thing, though, about his particular theory is I like theories which are able to be falsifiable. And at the moment, there's absolutely no way that you can do this. You can't really allege that there's a flaw in it. You may just say, well, I don't believe it. The only thing you can do is argue, as he did, that he doesn't believe any of the other theories are viable. Now, why this has become an issue is that there is a feeling among some parts of the scientific community that in his relations with the public press or in his popular book, which he's published, that he's been, shall we say, a little too enthusiastic in promoting this idea. I actually asked two scientists whom I have a very, very high regard for what they thought of how he had gone about this and whether he had violated any of these scientific norms. One of them thought, no, I think it's just fine. I think he's doing a very honest, objective presentation. The other equally highly regarded scientist thought this fellow is a self-promoter. It was disgraceful what he had done. I think there's a little bit to be said on both sides. Avi Loeb's complaints is that what he would call the scientific elites are just a bunch of old fuddy-duddies, and they're not willing to entertain any unusual theories. When I was just beginning my career, I had some senior scientists tell me that, Ray, this business about black holes and quasars, that's just nonsense. Don't waste your time on that. And now we know that those two areas are very, very important in fruitful areas of research. So there's something to be said about his complaint. On the other hand, I have to say that he probably did paint this as a too certain proposal. The very title of his book, it's Extraterrestrial, the first sign of intelligent life beyond Earth. That to me suggests that we really do have a positive sign of intelligent life beyond Earth. And of course we don't, it was just a suggestion of his. I would have felt much more comfortable had he said, Oumuamua, could it have been a sign of intelligent life beyond Earth? Question mark. With that, I think he would have avoided a lot of this criticism. Why is this important that people do adhere to scientific norms? And the way of doing science is publish in a peer-reviewed journal and let the critics have their criticism of it. If it passes review, then it's published and other people can respond to it. But be careful when you go to the press advocating for your own theories too vociferously or too enthusiastically. Why is this important? It's important because right now in society, we are faced with having to get the very best input on important scientific issues that are facing us. Climate change, for example. Scientists understand this. They know what needs to be done about. And if there's even a whiff of anything that seems like it's self-serving, that would be very, very bad. The similar thing arises now with the pandemic and vaccines. We must have absolute faith in the integrity and the objectivity of sciences. And so that's why I've gone out of my way to say a few words about this. And with that, I will stop the sharing and we'll see if you folks have any questions. I appreciate your patience in listening to this. And as I say, this is being recorded. Those of you friends who didn't get to watch it now can watch it later. And I'll try and elaborate on some of these points when I post it. Okay.
All right, Dr. Weymann, thank you very much for that presentation. That was very interesting. And I will go ahead and start right into some of the questions. And the first question that I want to bring up is, do we know how fast Oumuamua was moving when we detected it?
I don't have that number off the top of my head. It was obviously faster than the 27 kilometers or 26, whatever it was, which is the velocity would have when it first entered the solar system and when it was going to leave it. So it was in the process of decelerating. We could figuring it out by that trajectory. We know how far it is over the timelines that I had posted on its trajectory. And we know the time interval and we know the distance. And I'll look it up if you're interested. How fast.
Thank you.
Let me take a guess and say it was maybe moving 40 kilometers per second. It was about 85 when it passed the sun.
Okay. All right. That's fast.
Yes.
Are we still tracking it or is it out of range?
No, it's I mean, we know where it is, but it's way too faint now to observe.
Okay. In the observations, did they notice any particular colors on the object?
Yes, it was sort of reddish, which is not different from what you might have expected from an object which had been weathered. I mean, interstellar weather on its travel through space. It did have sort of a dull reddish hue.
Okay. How were they able to detect that? Do you know what instruments were involved in?
Well, you could take photographs with different colored filters and infer that that way.
All right, very good. And so here's another question. Does the motion close to the local standard of rest imply a possible origin in the local star cloud?
Oh, that's a really good question. It has to do with, can we actually trace it back to find out, oh, it came from that particular star? Uh, the answer is no. It's just not possible to do that accurately enough. Now, the people who have proposed the molecular hydrogen model have said, I think it came from a giant molecular cloud. It's called the Carina Columba cloud, but without referencing any particular star, because in their case, I want to emphasize, in their origin, it doesn't come from a star. It comes from the innards of this giant molecular cloud. Um, as you know, some of you, there's been a European satellite which has gotten exquisitely accurate three-dimensional velocities and distances of stars, a large number of stars. And there are some people who think that it may be possible to have some guesses about what a parent star could have been. I want to say just another word, though, about this question of how it could have arisen that it was so close to the standard of rest. What happens, again, let's talk about the hive of bees. The bees start out just on their little swarm, and then they get kind of agitated as things go on. When the star cluster is born, all the stars are moving more or less with this local standard of rest. But as they pursue their orbits around the galaxy, other stars jostle them a little bit and impart increasingly larger random velocities. And so if you want to explain, other than originating in this giant molecular cloud, why this object had a velocity that is so near the standard of rest, you would say that its host star was a fairly young star, and it did not have time to acquire the random velocities, taking it away from the local standard of rest.
So person online would like to know, where do you stand in the theories? Do you have a favorite?
I don't. I still like this tidal fragmentation model. I understand there are difficulties energetically with the water ice. We know there's an awful lot of water ice around. We know there's some solid nitrogen. We've never seen any solid hydrogen, and for that matter, we've never seen an alien spacecraft. So I guess I lead a little bit to the water ice and the nitrogen model, but certainly don't want to rule out the hydrogen model, although I think it's tough to get things really that cold. It takes some rather special circumstances.
Very good. All right. Well, that concludes the questions that we have. So I want to thank you again on behalf of Central Coast Astronomical for this wonderful presentation. And I know I'm going to go back and look at it again. There's a lot of great information. And I just want to remind everyone that at the beginning of the presentation, Dr. Weymann provided some contact information on the slide. And then if I would too, put an invitation out here as we're ready to conclude. Let us know what you thought of the presentation in the chat. Those chat messages are saved, and then we can pass those on to Dr. Weymann as well. So any final thoughts or words before we conclude?
No, I just hope all of you who are astronomers will be talking to public citizens about science, the value of science. And I invite you, if you're interested in the topic of climate change, to visit my website and learn about climate change. It's really, really an important topic. We need to do something about it.
All right. Well, thank you very much. And I hope, Dr. Weymann, I hope you and everyone online have a great evening or a great day, evening, morning, whenever you happen to watch this as a recording. So take care. And by the way, as you're watching this on a recording, if you'd like more information on Central Coast Astronomical, please visit our website, which is centralcoastastronomy.org, or you can follow us on YouTube and on Facebook as well. So thanks and good night.